All right, 5.2, we're going to finish this section today on multiplication and division of integers. And we had left off last time, and we were going to take a look at this time properties of multiplication. So integer multiplication. Now, as we look through these, you're going to be like, haven't we already done this before? And the answer is yes, we basically have. We did multiplication properties for whole numbers, and most of the multiplication properties for integers are exactly the same. There's very little difference, and so it will feel like we've already done this before. The first one is the closure property of multiplication. The closure property says that when you take two numbers and you multiply them together, you get another, I should have said that way. When you take two integers and you multiply them together, you get another integer. So A times B is a unique integer. Okay, so for integers A, B, and C, A times B is a unique integer. The commutative property says the order in which we multiply doesn't matter. So if you have A times B, it's the same thing as B times A. Okay, we've talked about the commutative property. The associative property holds. So we have A times B times C. We could multiply the A and the B first and then multiply by the C and we'll get the same result. So how we put those parentheses in there and which piece of the multiplication we do first is irrelevant. We get the same value. All right, the next three is the identity property of multiplication. So you guys just got back a test, and on the test, one of the things I asked you was which of these different operations have identities, and multiplication has an identity element. The identity element's the number 1. And so if we're saying that this has an identity, which it does, that would be the same number. So 1 is the unique identity element. And the reason is because 1 times any number A is the same as A times that 1, and it is equal to A. We have the distributive property of multiplication of integers, and this property says that if we have a number A and it's being multiplied by a sum or a difference, right? So a plus or a minus of C, then this is the same thing as A times B plus or minus A times C. And while it works from the front end, it also works from the back end. So if the B plus or minus C had come first, like this, the result would still hold. So if you would like to keep the order the same, you can do BA plus CA so that you're moving from left to right, right? B times the A, C times the A. But if you want to write it as AB and AC, that's fine too. Doesn't matter. That's a distributive property. And the last one, the zero property of multiplication property, says that what happens when you multiply by 0? You get 0, exactly. And it's unique, right? So 0 is the unique integer. Such that 0 times A or A times 0 is 0. Okay, those are all properties we've done. We've talked about them, maybe in a slightly different imagery, but this is the same list that we had when we did multiplication for whole numbers. All right, so we're going to take a minute. I want you to identify which property is being listed in 1 through 4, or A through D, I guess it's listed. Once you have your list and you've identified what you think it is in A, B, C, D, turn to a neighbor and just check and see if you got the same things. And then we'll come back together and make sure that everybody has the same. If you haven't already, check in with the neighbor, see if you agree or if you disagree, maybe discuss why you're getting different results. Okay. Most of the conversations died down, so you must have gotten your things written down. What did you guys decide the first one was?
Closure.
Yeah, it's closure. It's telling you that those two numbers, when they're multiplied, are an element of the integers. I should probably mention that your book uses I for integers. I think that I usually say that back in section 5.1, and I don't think I did that at all. It usually uses I for integers. It may have been on a video posted that you guys watched. Most books don't use I for integers. That is not the normal thing for people to use. Usually the letter Z is used, just so you know. If you were to ever see that in any other book anywhere, that's the typical one that's listed. And part of the reason why is because I also could stand for irrational, and that's another type of number. It can be a little bit confusing, so the I is not used. Just FYI. Your book uses it though, so we'll use it, but I just want you to be aware. How about the second one? Which one was that one?
Zero multiplication.
Yeah, the zero multiplication. How about the third one?
Distributive.
Yeah, it's distributive. And D.
Commutative.
Yeah. So that's what I was going to say. Commutative and associative, sometimes the default for us to think is that because there's parentheses, it has to be associative, but associative has to have three numbers being multiplied. This one only has two. The other thing about associative is associative doesn't change the order of the numbers. Commutative does. So if you're seeing the numbers flip spaces, like, they turn around in terms of what's listed first or second, that's going to be a commutative property. So this one's commutative. All right, we have a few more details to take a look at in this section, theorems and so forth. So here's our first one. Theorem 5.6 says, for every integer a, if we multiply by -1, negative a times 1, we get negative a. Okay, so every integer has this ability that we can multiply by the negative and we call it an additive inverse, okay? Theorem 5.7 talks about what happens when we multiply by anything else that's not a -1. It's just a negative value. So for integers a and b, if you have a negative a times b, that's the same thing as multiplying the a and the b and pulling the negative out in front. That's almost like an associative property, if you think about the negative being a representative at -1. And then the second piece on that one talks about what happens when they're both negative. So if a is negative and b is negative and we multiply them, the negative times the negative is going to be a positive. And we looked at that from perspective of the chip model last time and how we could sort of think about that, as well as from the other models, the charge fields model and the number line model. And then theorem 5.8 has a distribution property. So this distribution property is associated with the same thing that we had done before. I put mine all in the same place, put plus or minus in there, but the subtraction works as well here. So if we do a times b minus c or b minus c times a, it distributes through. It's not any different than our distributive property. It's listed in a slightly different way. All right, so let's take a look at the next page. Integer division. So for all integers a divided by b is the unique integer c, if it exists, such that a equals b times c. And this is much like what we did when we did whole number division. It looks a lot like the subtraction property when we do whole number subtraction and integer subtraction. All it's telling us is that if I do a divided by b and it's going to equal to c, this is the same thing as b times c equals to a. And to see it in an example kind of form, if I did, we'll do 6. 6 divided by 2 is equal to 3. And the reason is because 6 is equal to 2 times 3. So it's just asking us what would I have to multiply 2 by to get 3? Multiply 2 by to get 6. I'd have to multiply it by 3. So that's the answer to that division problem. Now, we did a whole, would say a whole chapter, but it's a short chapter. Chapter 4 was sections 4.1, 4.2, 4.3. We did a whole chapter about divisibility, all right? And it was specifically divisibility related to whole numbers. But everything we did in that section with divisibility related to whole numbers works with integers as well. So if we have divisibility for integers, it looks something like this. A divided by B is a unique integer. If that's a unique integer, then we'd say A is divisible by B, or equivalently, B divides A. So in very much the same way that we could write that 6 divides by 2, right? 6 is divisible by 2. I didn't write that right, sorry. 2 divides 6 is what I meant to write down. 2 divides 6. I could also write that negative 2 divides 6. And the reason that negative 2 divides 6 is because there is an integer that when I try to do 6 divided by negative 2, I get negative 3. Negative 3 is an integer, so it will be divide as well. It will be a divisibility process. Okay, what we're specifically trying to avoid or say doesn't work really is what happens when there's fractions or decimals when we try to do that. Okay. All right, integer inequalities. For all integers a and b, a is less than b, written a less than b, if and only if there exists a positive integer k such that a plus k is equal to b. This looks just like what we did when we did whole numbers, right? Are you seeing the theme for the section? Same song, second verse. Hardly any different than what we've seen before. Now, there are a few things, right? Like when we did this slide over here. Oops, this one right here. These are a little bit different. We didn't have negatives to contend with before. I mean, those are a little bit different. But a lot of the things we kind of get for free. Less than is one of them as well. And so we can say, for example, that negative 3 is less than 6. We would agree with that, right? And the reason that negative 3 is less than 6 is because there is a number that I can add here that will get it back up to 6. What would I have to add to negative 3 to equal 6? I'd have to add 9. So if I am able to find a value that works there and it's an integer value, which I am, then that negative 3 is in fact less than 6. And that number here is 9. So this works. I should have said this one too. It says it's a positive integer. I did skip over that. My 9 is definitely a positive integer, but I skipped over saying that. All right, inequality theorems. So for integers a and b, a is less than b, or we can say b is greater than a, if and only if b minus a is equal to a positive integer, i.e. b minus a is greater than 0. So a moment ago I said negative 3 is less than 6, right? So what this is saying is that this will work if and only if that 6 minus my negative 3 is greater than 0. And in fact, of course it is. So 6 minus negative 3 would be 6 plus 3. That's 9, and 9 is greater than 0. So it is correct to say that negative 3 is less than 6. Theorem 510 might be the most helpful in all the things that we're going to be working with in terms of you're going to go back to it and be like, yep, saw that used, yep, saw that used kind of thing. So let's take a look at it. The first one says, the details first say that x, y, and n are integers. So if x is less than y, then x plus n is less than y plus n. Right? So if we have two numbers and one's smaller than the other one and we add a little bit to each one of them, the smaller one is still going to be smaller, the bigger one is still going to be bigger. Makes sense, right? Think about salaries, right? If I make $15 an hour and RJ makes $10 an hour and we both get a $2 an hour bonus, right? I still make more than RJ does, right? It doesn't change the ratio between us, right? The difference between us, it's still going to be in the same situation it was before. All right, x is less than y, the second one, talks about what happens when we multiply by a negative number. So if I multiply by negative 1, it actually changes the direction of my inequality. So before it was less than and now it's greater than. And let me just write an example to the side so that you can see it work with numbers. So if, and I'm just going to use both of them positive and then we'll switch them both to negative because it's easier to see them that way. So if 2 is less than 3, which we would agree is, right? Then negative 2 and negative 3 have the reverse relationship. And thinking about it from a number line, I think, is probably one of the easier ways to think about that. So if 2 is less than 3, which would look like this on a number line, here's 0, then my negative 2 is here and my negative 3 is here. And in terms of a number line, less than means it's further to the left. So over here, the negative 3 would be smaller than the negative 2, or equivalently, we can say that negative 2 is bigger than negative 3. Okay? So I actually just had somebody in my Calc 3 class remind me, they were like, remind me, when was it that I switched the direction of an inequality? It's when you multiply or divide by a negative. That's the kicker, okay? Otherwise, you add and subtract things, doesn't change anything, but when you divide or multiply by a negative number, that changes directions of inequalities. All right, next one. There's 2 more. The next one says, if x is less than y and n is greater than 0, then if I multiply by n, it will keep the direction of the inequality. Now, this is happening because the n value is positive, right? So if I had 2 less than 3 and I multiply both of them by 2, well, 4 is now less than 6. No problem. Okay, so you multiply by a positive number, the direction of inequality stays the same. But on the 4th one here, if you multiply by a negative number, what's the direction of the inequality going to do? It's going to flip. Okay? And this is just a more generalized case of the second bullet point here. The second bullet point says what happens if you multiply by negative 1. The 4th one says what happens if you multiply by negative anything else. Okay, well, it's going to do the same thing. It's just going to change the direction of the inequality. Okay? The n's still show up, though, right? So it's xn and yn. Okay, let's take a look at a couple of examples. There's more than one way to do these problems. You can do them from a very hardcore traditional algebra point of view. That's totally fine. There's nothing wrong with that. These are like end of algebra 1 kind of things. You can do them by trial and error as well, sort of like observing and saying, I think it's going to look like this. Let's test and see if that works. That's fine. So let's take a look at what we have here. This is example 5. Find the integers that make the following true. The first one says negative 5 times x minus 3 is equal to negative 5. So let me show you what I would think that you would be doing if you were doing this from a observational point of view, okay? And then I can show you from an equation point of view and you can pick which one you like. Does that sound fair? Okay. So if you take a look at this and you compare the pieces that are the same, this, whoops, that was supposed to be a highlighter. This piece and this piece, they match, correct? What that means is it means that this piece in between here, it has to be equal to 1 because that's the only thing I could multiply it by and the values stay the same on both sides. I need to multiply negative 5 by something on the left so that it's still equal to negative 5. Are you with me? So this thing would have to equal 1 in order for that to happen. Well, okay, what does x have to be for that quantity in the parentheses to equal 1? 4. X would need to be 4 for that to happen. So we're not really solving an algebra problem if we think about it that way. I mean, we are, but we're not doing it from a traditional algebra approach. It's more from a recognition of what's happening here approach. And you don't have to like that approach. You don't have to use that approach, but it is a valid approach to use, okay? If you would like to do this from a more traditional algebra approach, you can actually start and you can take a look at, distributing the 5 through. So we can distribute our negative 5 through. So this is negative 5x, and then we have to do plus 15, right? Negative 5 times negative 3 would be positive 15 equals negative 5. What would be our next step in algebra to do here? Yeah, we would move the 15, and we will do it with subtraction. So I still have a negative 5x on the left. These add to 0. What do I get on the right? What's negative 5 and negative 15?
Negative 20.
Negative 20. Then what?
Divide.
Divide by negative 5. Now, a negative divided by negative gives me a positive, and 20 divided by 5 gives me 4. Okay, so this is a more of traditional algebra perspective, which I've told you all the way along. You can use algebra in this course. It's not that I'm trying to discourage you from doing it. But I do want you to realize that there are things that show up in younger, books for younger kids where they're not expecting them to do this. So if you go into that book and you're trying to think about algebra and how am I going to explain this to my kids, that's probably not what the book intended for you to do. There was probably some other intention behind a problem like that. And it's probably more likely that it would be the top approach that they would be intending for. But you can do either one for me. Okay? Ready for example 2? Well, I know it's not 2, but whatever it is. The second one on this page, B. All right, so taking a look at this one again, we'll do it first from the perspective of what happens from a observational point of view, and then I'll look at it with you from an algebra, like a true algebra standpoint, okay? So take a look at what's happening on the left and the right. They're both squared, right? They're both squared, okay? Well, what's happening inside the parentheses? Say again? There's subtraction. Can you compare from the left to the right what's being subtracted?
1 and x.
1 and x. In both cases, right, RJ?
Yep.
Yeah. So on one side, we have, let me see which order it is, x minus 1. On the other side, I have 1 minus x. It's the same quantity, but it's flipped around, right? I've flipped the subtraction. Okay, so let's just think about some numbers for a second. If you do 5 minus 3, and then you do 3 minus 5, what happens?
You get 2 different numbers. One of them will be positive, the other will be negative.
Okay, so you get 2 different numbers, one's positive and one's negative. What's the same?
Division? It's the same number.
It's the same number, yeah. So, like if we had, I'm going to do an example here, the one I just said. 5 minus 3, 3 minus 5. We have 2 and we have negative 2, right? Okay, so one's positive, one's negative, as we've mentioned. They are different values, that's true. But if you ignored the signs, would they not be the same? They would. They'd be the same, wouldn't they? Yeah, so they'd be the same thing. So if I take the number on the left and I square it, what would I get? 4. And if I take the number on the right and I square it, what would I get? 4. Now what can you tell me about those numbers? They are the same number. Now there's nothing special about 5 and 3. Those were arbitrary picks that I made, right? They were. I just chose random numbers. Something small. I was looking for something small, I suppose. But other than that, there's nothing special about those numbers. So what happens when I take a number and I take 2 numbers, and I subtract them, and then I square them, or if I take those numbers and I subtract them in the wrong order, so to speak, or the opposite order, and I square them, I get the same quantity. Any idea what that means that x is going to equal here?
Any positive number.
It is. And it's not just positive, though. It's more broad than that. X is any integer. Anything works. So pause for a moment and just try a couple things. I'd like for you to develop the idea that this makes sense before I move on and show you an algebra approach, okay? Try a couple things with the exact values we were given, not the made-up stuff I was making up, but up here. Try a couple things for x. Try positives, try negatives, try zeros. What happens? You get the same thing every single time, okay? So trying numbers inside of an equation is not always a terrible approach. It develops in us some intuition of what's happening with the expressions that we're given. Now, let's take a look at this from a more algebra-like approach, since we were looking at that as well, okay? So if we think about this more like from algebra, then the first thing that would happen on the top, well, we could do a couple of different things. Let me show you one option and then I'll mention a second option. One option on the left-hand side would be to actually multiply these out. And on the right-hand side to do the same. This would be the better of the two options I'm going to show you because it will not lead you astray. We'll say that. So if I do this, I'm going to have to FOIL this out or distribute. So this is going to give me x squared minus x. And then I have another minus x and plus 1. On the right-hand side, we'll do the same thing. So I have 1 minus x. And I have minus x, plus x squared. What do you notice?
the same, or the
Yeah.
same factors, just arranged in a different way.
Yeah, that's true too. Okay, so every single piece is the same. They're just in a different order of addition. And we know from working with properties of addition that the order of that, the commutativity, is a property that we have, so we can switch orders around. So if we were to manipulate this, clean it up a little bit, this would say x squared minus 2x plus 1 on the left. And on the right, again, shifting orders around like RJ mentioned, it would also be x squared and then minus 2x plus 1. They're exactly the same. So what does that mean? Well, it means that no matter what x is, I'm going to be putting it into the same expression on the left and on the right, identically the same, which means x can be any number I wish, not even just only integers. It could actually be, fractions and square roots and things too, and it would still work. We're only working with integers. So when we say this, we'll still say that x is an integer. Okay, I do want to show you one other thing that can throw you on this particular problem, because I don't want you to think that I don't want you to think I'm not aware that this is an option, because it does show up and it looks a little bit tempting to do. Did anybody look at this and say, just take a square root? Yeah, it looks really tempting. And let me show you the caveat to doing that, why you have to be careful. When you take a square root and you put the square root in, what you might remember from an algebra course somewhere along the way is that you have to put a plus or a minus on it. So you actually end up with two different equations, which is not nice. It's not as nice as the other way we did it. So one option is you end up with x minus 1 is equal to 1 minus x, and the other option you end up with is x minus 1 is equal to negative 1 minus x. And you have to solve two things now. Well, on the first one, if I add my 1, this gives me x, whoops, that's a 1, equals 2 minus x, and I add my x. And this gives me 2x is equal to 2, and I divide by 2. It looks very much like x is equal to 1, and x equal 1, of course, will work. There's nothing wrong with that answer. It will work. But on the left-hand side, when we distribute the negative through, we get this. And much like the problem we looked at before, if we reorder it, we find out from this situation that x is any integer. But can you see what the pitfall is for most people if they try to do this? It's leaving off the plus or the minus. And if you leave off the plus or the minus, what will happen is you'll only get this part of the answer, and you will think that the only value that works is 1, but it isn't. All values will work. So be careful when you're thinking about things from taking a square root point of view. That might not yield what you were expecting it to yield.